Hey guys, Gene here. Welcome back to Do Some Dev. Today we're diving deep into the world of concurrency, that intricate dance of tasks happening seemingly all at once. For years, Java developers have navigated this landscape with traditional platform threads. But what if I told you there's a new way to approach this? A lighter, more efficient way that's shaking things up. This isn't just another incremental update. It's a fundamental shift in how we think about and build concurrent applications in Java. So buckle up, because we're about to explore one of the biggest and newest topics in Java multithreading, which are virtual threads. If you're just joining our Do Some Dev community today, welcome. To truly appreciate the advancements we'll explore today, I highly encourage you to check out the preceding 12 Java multithreading videos in the series. You can find them in the Java Advanced playlist. They come from a cohesive exploration, building a robust foundation that will enrich your understanding of virtual threads and broaden your overall experience in concurrent programming. I will also post a link in the video description. As always, the code demonstrated throughout this video is readily available on GitHub. Dive in, explore, and feel free to adapt it for your own projects. The link to the repository can also be found in the video description. Virtual threads became a final feature in JDK 21, which was released in September 23. Therefore, it's fair to say that virtual threads are a hot and new topic. To begin our journey, we'll meticulously unpack the fundamentals of virtual threads. We'll explore their architecture, how they differ from traditional platform threads, and the core principles that underpin their efficiency. The aim of this video is to ensure that everyone, regardless of their prior experience with concurrency, gains a clear and comprehensive understanding of this exciting new technology. But our exploration won't stop at theory. I firmly do believe that true understanding comes from application. That's why we'll transition into the practical realm, crafting a step-by-step Java example that brings virtual threads to life. You'll witness firsthand how to harness their capabilities to build more responsive and scalable applications. We'll dissect various use cases, demonstrating precisely where the adoption of virtual thread yields the most significant performance gains and unlocks new possibilities for our Java projects. Specifically, we'll build a practical code example to compare traditional platform threads, often used with thread pools, against virtual threads, highlighting the clear benefits and simpler programming model that virtual threads provide. Alright, if you find this deep dive into virtual threads insightful and valuable, a simple thumbs up is greatly appreciated. It helps others discover this content and supports the work that is done here at Do Some Dev. Additionally, your thoughts and questions have a place here. Just ask whatever you're not sure of and seek an answer for in the comment section of this video. Other viewers reading your comment might give you an answer, and I also will do my best to answer in a timely manner. Also, feel free to share any experiences you've had experimenting with virtual threads in your own projects. Your insights could be incredibly helpful to fellow developers. With that said, let's dive into the fascinating world of Java virtual threads. Alright, let's quickly delve into the foundational concept of traditional Java threads. To truly appreciate the significance of virtual threads, we must first understand the mechanics and the limitations of their predecessors. So let's begin by exploring what traditional Java threads are all about. At their core, traditional Java threads are intrinsically linked to the operating system's threads, often referred to as OS threads or native threads. When you create a new thread in Java, or when you utilize constructs like execute a service with its default thread pool, you're essentially requesting the operating system to create and manage a corresponding native thread. Think of OS threads as the fundamental unit of concurrency at the operating system level. The OS scheduler is responsible for allocating CPU time to these threads, allowing them to execute their task. Now let's explore how these OS threads work. The OS maintains a scheduling algorithm that determines which thread gets run on a CPU core at any given moment. This involves a process called time slicing, where each thread is given a small slice of CPU time before the scheduler potentially switches to another thread. This rapid switching gives the illusion of multiple tasks running in parallel, even on systems with a limited number of CPU cores. The OS manages the state of each thread, meaning running, ready, blocked, and terminated. It also handles context switching between threads and allocates the necessary resources such as stack space and kernel-level data structures. However, this tight coupling with OS threads comes with inherent limitations. One significant challenge is blocking. When a traditional Java thread performs an operation that requires waiting, for example, reading from a network socket, accessing a database, or waiting for a lock to be released, the underlying OS thread becomes blocked. During this blocked period, the OS thread sits idle, consuming system resources, which is primarily memory for its stack, without making any progress on the application's tasks. While one thread is blocked, it cannot be used to execute other tasks. In high concurrency scenarios, a large number of blocked threads can lead to a significant resource wastage and hinder the overall throughput of the application. Another crucial limitation is resource consumption. Each OS thread requires a certain amount of memory to maintain its stack. The stack size is typically configured at the OS level or JVM level and can range from a few hundred kilobytes to a few megabytes per thread. In applications that need to handle a large number of concurrent operations, creating a corresponding number of OS threads can quickly exhaust system memory, leading to out-of-memory error exceptions and instability. Furthermore, the creation and destruction of OS threads can be a relatively expensive operation in terms of system resources and time. Finally, context switching is a performance consideration. When the operating system switches from one running thread to another, it needs to save the state of the current thread, meaning registers, program counter, stack pointer, and so on. It also needs to load the state of the next thread to be executed. This context switching operation has an overhead. While the time taken for a single context switch might be small, in heavy loaded systems with a large number of active threads, the cumulative effect of frequent context switching can consume a significant portion of CPU time, leaving less time for the actual application work. The fundamental characteristic of traditional Java threads is their one-to-one mapping to OS threads. For every Java thread you create in a traditional sense, there is a direct underlying OS thread managed by the operating system. This direct correspondence is the root cause of the limitations we've discussed. The lifecycle, scheduling, and resource management of the Java thread are inherently tied to those of its underlying OS thread. Understanding these aspects of traditional Java threads, their direct reliance on OS threads, how they function within the OS scheduling framework, and the limitations they face due to blocking, resource, consumption, and context switching, sets the stage for appreciating the innovations and advantages that virtual threads bring to the realm of Java concurrency. In our next step, we'll explore how virtual threads offer a different paradigm to address these very challenges. Continuing our exploration, we now arrive at the crucial question, why do we need something like virtual threads? The answer lies primarily in the scalability issues encountered when using traditional threads in high concurrency applications. As we discussed, each traditional Java thread maps directly to an OS thread. While this model works reasonably well for applications with a moderate number of concurrent operations, it starts to show its limitations as the demand for concurrency grows. Imagine a modern web server handling thousands or even tens of thousands of concurrent client requests. If each request were to be handled by a dedicated OS thread, the sheer number of threads would quickly overwhelm the system. The problems we touched upon earlier become significantly amplified in such high concurrency scenarios. The resource consumption of maintaining a large number of OS threads, each with its own substantial stack space, can lead to memory exhaustion and application crashes. The context switching overhead between thousands of active threads becomes a major bottleneck, consuming a significant portion of CPU cycles that could otherwise be used for processing actual work. Furthermore, the prevalence of blocking operations in typical I/O-bound applications like web servers waiting for network requests or database queries means that a vast majority of these OS threads could be sitting idle, wasting resources while waiting for I/O to complete. This scalability challenge has been a persistent concern for developers building highly concurrent Java applications. Techniques like thread pooling were introduced to mitigate some of these issues by reusing a limited number of OS threads for a larger number of tasks. However, thread pools introduced their own complexities, such as managing pool sizes, handling blocked tasks, and the potential for thread starvation. Even with careful tuning, thread pools built on traditional threads don't fundamentally address the one-to-one mapping and the associated OS level overhead. This is where the concept of lightweight concurrency comes into play, and this is the problem that virtual threads are designed to solve. Lightweight concurrency aims to provide a way to handle a massive number of concurrent tasks without the heavy resource footprint and overhead associated with traditional OS threads. The core idea is to decouple the execution of a concurrent task from the underlying OS thread. Instead of having a dedicated OS thread for each concurrent operation, lightweight concurrency models allow a single OS thread to efficiently manage and execute a much larger number of concurrent tasks. These lightweight entities can be created and managed much more cheaply than OS threads, both in terms of memory consumption and the time it takes to create and destroy them. Furthermore, when a lightweight task needs to perform a blocking operation, it can often be suspended in a way that doesn't require the underlying OS thread to be blocked. This allows the OS thread to continue processing other active tasks. Virtual threads are Java's answer to this need for lightweight concurrency. They provide a way to achieve high concurrency without the limitations imposed by the direct one-to-one mapping to OS threads. By introducing a new level of abstraction between the concurrent task in Java and the underlying OS thread, Java virtual threads aim to dramatically improve the scalability and efficiency of Java applications, especially those that are I/O bound and require handling a large number of concurrent operations. Alright, let's now make sure that we understand the essence of virtual threads and understand how they differ from their traditional counterparts. To grasp this new concept, it's helpful to think in terms of analogy. Imagine a stage play. In the world of traditional threads, each actor would have their own dedicated stage crew member, following them around, ready to assist with every action, even when the actor is simply waiting backstage for the next scene. This one-to-one relationship can become quite resource intensive if you have a large cast with many actors spending a lot of time waiting. Now consider virtual threads as a different approach to managing this play. Instead of each actor having their own dedicated crew member, you have a smaller number of highly skilled stagehands, let's call them carrier threads, who efficiently manage a much larger number of actors, the virtual threads. When an actor needs to perform on stage, a carrier thread picks them up and runs their scene. If the actor needs to wait backstage, they can be efficiently parked without tying up a dedicated stagehand. The carrier thread is then free to pick up another actor and continue the performance. This is the fundamental idea behind virtual threads. They are lightweight, user mode threads managed by the JVM. The core difference lies in the many-to-many mapping between the virtual threads and the underlying OS threads. Instead of a one-to-one relationship, numerous virtual threads can run on a much smaller pool of OS threads, which are now referred to as carrier threads. The JVM intelligently schedules and manages the execution of these virtual threads on the available carrier thread. When a virtual thread performs a blocking operation, it doesn't necessarily block the underlying carrier thread. Instead, the JVM can park the virtual thread, allowing the carrier thread to continue executing other virtual threads. When the blocking operation completes, the virtual thread can be unparked and resumed on any available carrier thread. This decoupling from the direct OS thread mapping is the key to the efficiency and scalability of virtual threads. Because virtual threads are managed by the JVM, their creation and management are significantly cheaper than that of the OS threads. You can create millions of virtual threads without the same resource constraints associated with creating millions of OS threads. The memory footprint of a virtual thread is also considerably smaller compared to the stack space required by an OS thread. Crucially, virtual threads are managed by the JVM, not the operating system scheduler. The JVM has its own scheduler that efficiently multiplexes a large number of virtual threads onto a smaller number of carrier threads. This user-level scheduling is much faster and more lightweight than kernel-level OS scheduling. The JVM is aware of when a virtual thread is about to perform a blocking operation and can orchestrate the parking and unparking of these threads to maximize the utilization of the underlying carrier threads. In essence, virtual threads provide a way to write concurrent code in a straightforward thread per task style, but without the scalability limitations of traditional OS threads. Developers can create a new virtual thread for each concurrent operation without worrying about exhausting the system resources. The JVM takes care of efficiently mapping those virtual threads onto a limited number of OS threads, handling the complexities of scheduling and I/O operations under the hood. This paradigm shift allows for much higher concurrency and improved application responsiveness, especially in I/O-bound applications, which we will explore further with a practical example in this video. Now let's take a look at the key benefits of virtual threads. This is where we truly understand why this innovation is a game changer for Java developers. Virtual threads bring a fresh perspective to concurrent programming, offering substantial benefits that address the limitations of traditional threading models. First and foremost, virtual threads deliver increased throughput. This means your application can handle a significantly higher number of concurrent tasks. Imagine the web server we talked earlier about, juggling thousands or even millions of incoming requests simultaneously. With traditional threads, you would quickly hit a ceiling due to resource exhaustion and the overhead of managing a vast number of OS threads. Virtual threads, however, allow you to scale your application's capacity dramatically, ensuring that you can process more operations concurrently without overwhelming your system. Secondly, a major benefit is reduced resource consumption. Traditional Java threads are tightly coupled with OS threads, each demanding a substantial amount of memory for its stack, which, as mentioned earlier, typically ranging from hundreds of kilobytes to a few megabytes, quickly leading to an out-of-memory error exception in high concurrency scenarios. Virtual threads, in contrast, are lightweight and JVM managed. Their memory footprint is considerably smaller, allowing you to create millions of virtual threads without the same resource constraints. This efficiency translates directly into more stable and scalable applications. Thirdly, virtual threads offer simplified concurrent programming. For years, developers have struggled with the complexities of managing thread pools and dealing with blocking operations in traditional multithreading. When a traditional Java thread performs a blocking operation, like waiting for network I/O or a database connection, the underlying OS thread becomes idle and consumes resources without making progress. This forces developers to adopt complex asynchronous programming models to avoid blocking precious OS threads. With virtual threads, you can write straightforward blocking-style code, and the JVM intelligently handles the parking and unparking of virtual threads without blocking the underlying carrier threads. This drastically simplifies your code, making it more readable and maintainable, while still achieving high concurrency. You no longer have to sacrifice code complexity for scalability. Finally, virtual threads lead to improved responsiveness. In applications under heavy load, traditional threading models can suffer from significant context switching overhead and resource contention, making the application feel sluggish. Since virtual threads are managed by the JVM's own lightweight scheduler, and they can be efficiently parked and resumed without tying up carrier threads, your application remains responsive even when handling a massive number of concurrent operations. This enhanced responsiveness translates to a smoother user experience and more efficient resource utilization. These key benefits of increased throughput, reduced resource consumption, simplifies concurrent programming, and improved responsiveness collectively make virtual threads a transformative feature in Java. They empower you to build highly scalable, efficient, and easy to maintain concurrent applications, especially those that are I/O bound. Now, what new possibilities will you unlock for your Java projects by adopting this new paradigm? Let's now delve into the fundamental building blocks that underpin virtual threads, understanding the core concepts that make them so powerful and efficient. Grasping these ideas is crucial for truly leveraging virtual threads in your applications. The first essential concept is carrier threads. These are the traditional platform threads, the underlying OS threads, that actually execute virtual threads. Think back to our stage play analogy. If virtual threads are the actors, then carrier threads are the highly skilled stagehands. A smaller number of carrier threads efficiently manage a much larger number of virtual threads. When a virtual thread needs to run, a carrier thread picks it up and executes its task. This many-to-many mapping is the key differentiator from traditional threads, one-to-one relationship with OS threads. Next, we briefly touch upon continuations. While a deep dive into continuations is beyond the scope of this video, it's important to know that they are the underlying mechanism that enables the JVM to efficiently pause and resume virtual threads. When a virtual thread encounters a blocking operation, the JVM uses continuations to park the virtual thread, saving the state without blocking the carrier thread. This allows the carrier thread to immediately pick up another virtual thread and continue processing. When the blocking operation completes, the virtual thread can be unparked and resumed on any available carrier thread. This is how virtual threads achieve their incredible efficiency and scalability, especially in I/O-bound scenarios. Finally, it's important to understand the fork join pool integration. By default, the JVM leverages the common fork join pool to manage the carrier threads that execute virtual threads. This integration means that the JVM can intelligently and efficiently schedule virtual threads onto a shared pool of carrier threads, optimizing resource utilization. This design choice further underscores the lightweight and efficient nature of virtual threads, as they seamlessly integrate with existing high-performance concurrency constructs within the Java ecosystem. These core concepts, carrier threads, continuations, and fork join pool integration, are the pillars upon which virtual threads are built. They represent a fundamental shift in how concurrency is managed in Java, enabling developers to write highly concurrent applications with unprecedented ease and efficiency. Ready to discover how mastering these principles can empower you to create high-performing, scalable Java systems? Let's move into the practical realm and explore how to create and use virtual threads in your Java applications. One of the greatest advantages of virtual threads is their ease of use, often requiring minimal changes to existing code for I/O-bound operations. Java provides several straightforward ways to instantiate and manage virtual threads. The most direct approach is using thread.startVirtualThread. This static method allows you to immediately create and start a new virtual thread with a given runnable task. For more fluent and configurable creation, you can use thread.virtualStart. Most significantly, virtual threads integrate seamlessly with the executor service framework through executors.newVirtualThreadPerTaskExecutor. This executor creates a new virtual thread for each submitted task, freeing you from managing pool sizes or handling block tasks. Instead of a CPU-intensive task, which doesn't fully leverage virtual thread strength, let's demonstrate their power in a common I/O-bound scenario, simulating concurrent network calls. We will simulate a simple network call that takes a short, random amount of time to complete. We'll execute many such calls concurrently using both traditional threads via a fixed thread pool and virtual threads. Okay, now let's build ourselves an example in Java. So the first thing we're going to do here is define ourselves a class, I/O-bound task. This is a class where we want to define some input-output tasks. And because this is a simulation and we are not really doing input-output tasks, we will simulate the waiting time with thread sleep. But no worries, we will see that in a minute. So let's start by implementing runnable. And the first thing that we want to do here is create a little variable to remember the task ID, private final int task ID, which we'll fill using a constructor. Alright, because we implement the runnable interface, we also implement the runnable method, which also is the place where we define the actual work. So let's start with thread sleep to simulate waiting time, thread local random, current, next int between 50 and 200. What this does is create a random number between 50 and 200 and passes it on to the sleep method. So what we do here is simulate an I/O operation, waiting between 50 milliseconds and 200 milliseconds. For instance, network call or database query. Alright, this throws an error, so let's catch it. So we will run into this interrupted exception if the thread got interrupted. But the disadvantage is that this also swallows the signal, and because we want to keep this signal and send it to the caller of this run method, we will simply throw it again. Re-interrupt the current thread to propagate the interruption signal. Thread, current thread, interrupt. Let's also output the error. Task ID, interrupted. And that's all we need. Our next step will be to call this method quite a few times to get our simulation running. So let's go back to the main method. And because we will run other tests here as well, we also may want to have input from the user who chooses if he wants to run the input-output task or another task that we want to define later. So let's start. Read input from terminal. We will use a scanner for this. System input. Then we will tell the user what to do. Enter 1 for I/O test. Let's grab that. Input, scanner, next line. And now we can differentiate. If input equals ignore case, if he said 1, then go in here. And if not, tell it to him. Unknown selection, input. After having done that, scanner close to free the resources. Alright, now we want to have something to do here. So let's define a new method for that. Private static void run IO test. We will give it a name. And because we are comparing two types of executor services, namely the thread pool and the virtual threads, we also want to provide this as a variable. Executor service. Executor. Now let's put everything in here into a try-catch context. Interrupted exception. And if that happens, output error. Error interrupted. Now what we want to do here first is remember the start time. Long start time, system current time millis. And we will also want to remember the end time. Long end time, system current time millis. After having done that, we want to output statistics. Printing a line. Name from the parameters. Colon. End time minus start time. Milliseconds. Alright, now let's define the actual work. Submit tasks. Into a for loop. Int I. Let's start at 0. I smaller than. And here we need to define how many tasks we want to handle. So let's quickly create a variable for that. Private static final int number of tasks. And let's set it to 1000. Number of tasks in steps of 1. And in every iteration, executor submit a new task of IO bound task, submitting the current iteration as a task ID. After submitting the tasks, we wait for termination, executor shutdown, and executor await timeout, 1 minute. That's all we need. Let's put it together. Run IO tests, IO traditional, meaning executors new fixed thread pool. And we also need to provide the quantity of cores. For that, let's define a variable. Private static final int CPU cores. Let's get the maximum runtime, get runtime available processes, CPU cores. There we go. Now the second test, run IO tests, IO virtual, for the virtual test example, executors, new virtual thread per task executor. That's all we need to do. Now the only thing that remains is running the application. Run. And here I'm asked to enter which test to run. There is only one to choose from, so 1 and enter. And now the test is running. And in just a couple of seconds we will have the results of both tests running. And there we go. And here we can see that the traditional test with the fixed thread pool took 8 seconds to complete everything, while the virtual threads optimized everything down to 200 milliseconds, which is much faster. You can see that here. But don't just blindly believe my words. Go get the code and try it out yourself. This example directly demonstrates the core advantage of virtual threads, their ability to handle a vast number of concurrent I/O operations efficiently, simplifying your code by allowing you to write straightforward blocking style logic without the scalability limitations of traditional OS threads. So far, we've explored the incredible power of Java virtual threads and how they revolutionize handling blocking operations, making your applications far more scalable and responsive. But like any powerful tool, virtual threads have specific strengths, and it's equally important to understand where they are not the optimal choice. In this chapter, we're going to delve into scenarios where traditional platform threads, often managed in fixed thread pools, can still be just as, if not more, efficient. The key distinction here lies in the nature of the tasks themselves. While virtual threads excel when tasks spend a lot of time waiting for I/O, they don't magically speed up the work that is purely computational. To illustrate this, we'll examine a common CPU-bound task, prime number checking. This is an operation that continuously consumes CPU cycles without ever pausing to wait for external resources. We'll use this example to compare the performance CPU-bound when executed by a traditional fixed thread pool versus a virtual thread executor. As we go through the code, pay close attention to the execution times. You may find that the results are surprisingly similar, or even that the traditional thread pool holds a slight advantage. This demonstrates that the workloads dominated by raw computation, where threads are constantly busy and never block. The inherent scheduling overhead of virtual threads, however small, can mean that a lean fixed thread pool of platform threads remains highly effective and sometimes even the preferred choice. Let's dive in. Okay, now it's time to enhance our example a bit and add a test. So this time what we want to do is add a CPU-bound task. But let's first adapt our example. Enter 1 for I/O tests or 2 for CPU tests. Then we also want to differentiate it here. So let's add another if, else if input equals ignore case 2. And this is the place where we will put our next tests. Now let's first define the tests. CPU bound task. Again, here we will implement runnable. One of the ways to define a CPU bound task is by calculating prime numbers. And to define that, we're going to need a number, private final int number, which we will fill using a constructor. And because we implement the runnable interface, we also implement the run method. So to check for primes, let's define a method for that. Private boolean check prime. And let's provide a long n number. So the first thing is if the number is smaller or equal 1, we don't need to continue. We just return false. The next thing is that 2 and 3 are prime numbers. Therefore, we can return true. And same thing, if they are divisible by 2 or 3, we return false. Meaning if n modulo 2 equals 0 or n modulo 3 equals 0. If that happens, return false. Alright, the rest we can check from 5 onwards with a step of 6. Meaning we use a for loop, long I equals beginning at 5, I times I, smaller or equal n, I equals I plus 6. Now a little check, if n modulo I equals 0 or n modulo I plus 2 equals 0, then return false. Alright, and in case none of that happens, return true. Alright, that should keep the CPU busy. Now let's run it. Boolean is prime and provide the number. That's it. Now let's go back to the main method and see what we need. Here we need another method to run the test. So let's create one. Private static void run CPU test. A name. And like in the example before, executor service, executor. Let's put everything in a try catch. Interrupted exception. And if that happens, error interrupted. Now we start by remembering the start time. We can just copy it from the other example. We also want to remember the end time. And we need some statistics. And then we want to do some actual work, which consists of the same loop, but we call a different class, CPU bound task, and we want to provide a certain number. So let's define the number that we want to provide. It needs to be a number that's reasonably big. So private static final int prime number. Let's make it 1,000,000,000,000. That should be big enough. All right, let's provide it. Prime number. After having submitted the tasks, we also want to shut them down and await their termination. And that's about it. Now let's add it to the main method. Run CPU tests. CPU traditional. Executors new fixed thread pool. Providing CPU cores as the number of cores, which we defined to be the total number of cores that we have. And let's also add another one, run CPU, this time virtual, and executors again, new virtual thread per task executor. That's it. Now let's run the application. This time we're going to choose number 2 for the CPU test and enter. And there we go. Here we can clearly see that the virtual threads are not the better choice. In this example, it definitely comes down to using the traditional version, meaning executors new fixed thread pool, which in this case takes even less than half of the time that virtual threads take. But again, don't take my words for granted. Try it out on your own system. Go get the code on GitHub and try it out yourself. For CPU-bound tasks where threads are continuously active and not waiting for external resources, traditional platform threads in a fixed thread pool can be equally or more efficient due to the overhead of virtual threads scheduling. This distinction is crucial for optimizing application performance. Having clarified where traditional threads remain suitable, we will now examine how virtual threads specifically revolutionize the handling of block-in operations. Let's explore one of the most critical aspects of virtual threads, how they revolutionize the handling of block-in operations, which has historically been a significant challenge in concurrent programming. The primary innovation of virtual threads lies in how they handle I/O and other blocking tasks without blocking the carrier thread. In the world of traditional threads, when a thread performs a blocking operation, such as reading data from a network socket, waiting for a database query to return, or acquiring a lock, the underlying OS thread becomes idle. It sits there consuming system resources without making any progress on the application's task. This is a major source of inefficiency and scalability issues, especially in I/O-bound operations. Virtual threads solves this problem elegantly. When a virtual thread encounters a blocking operation, the JVM can park the virtual thread. This means the execution state of the virtual thread is saved and it's temporarily detached from its concurrent carrier thread. The carrier thread is then immediately freed up to execute another active virtual thread. This allows the limited pool of carrier threads to remain busy and highly utilized, maximizing CPU efficiency. When the blocking operation completes, the JVM unparks the virtual thread and it can be resumed on any available carrier thread. This decoupling is the key to virtual threads' efficiency and scalability. It is also important to understand the concept of pinning a virtual thread to a carrier thread. While the general rule is that the virtual thread can be parked and unmounted from its carrier thread during blocking operations, there are specific scenarios where the virtual thread might become pinned to the carrier thread. This means that the carrier thread remains occupied by that specific virtual thread, even during a blocking operation, preventing the carrier thread from executing another virtual thread. Pinning typically occurs when a virtual thread performs a blocking operation while holding a synchronized block or when it's executing native code. While the JVM attempts to minimize pinning, it's generally something to be aware of and, if possible, avoid in your application design, as it can temporarily reduce the benefits of virtual threads. However, for most common I/O operations, virtual threads handle blocking transparently and efficiently without pinning. In a sense, virtual threads empower you to write straightforward, synchronous-looking code for I/O-bound tasks without fear of exhausting your system's resources or introducing complex asynchronous callbacks. This fundamental shift in how blocking operations are handled is a cornerstone in the scalability and simplified programming model that virtual threads bring to Java. Let's discuss the best practices and key considerations for efficiently utilizing virtual threads in your Java applications. While virtual threads offer immense benefits, understanding their optimal use cases and potential interactions is crucial for maximizing their impact. First, it's essential to understand when to use virtual threads. Virtual threads are exceptionally well suited for I/O-bound tasks and scenarios requiring high concurrency. This includes common application patterns like web servers, handling numerous client requests, database interactions, external API calls, or message queue processing. In these situations, tasks spend a significant amount of time waiting for external resources like network data or database responses, and virtual threads' ability to park and unmount from the carrier threads without blocking them delivers massive scalability gains. Conversely, it's important to consider when traditional platform threads might still be more suitable. For CPU-bound tasks where computations are intensive and little time is spent waiting, the benefits of virtual threads are less pronounced. In such cases, the overhead of context switching, even with lightweight virtual threads, might not offer a significant advantage over a well-tuned pool of traditional platform threads directly managed by the OS scheduler. For CPU-bound operations, you still want to ensure that your application doesn't create more active threads than available CPU cores. When it comes to monitoring and debugging virtual threads, while the experience is largely similar to traditional threads, there are nuances. Standard Java profiling and debugging tools generally support virtual threads, allowing you to inspect their state, stack traces, and execution paths. However, given the sheer number of virtual threads that can exist, understanding how they are multiplexed onto carrier threads and identifying potential pinning situations becomes a new dimension of monitoring. Tools will continue to evolve to provide a more specific, insightful virtual thread behavior. Finally, a brief consideration for interaction with thread local variables. While virtual threads aim to simplify concurrent programming by providing a thread per task model, it's important to remember that thread local variables are, as the name suggests, local to a specific thread instance. When a virtual thread is parked and unparked, it's still the same thread instance, so thread local variables behave as expected. However, overuse of thread local variables, especially in applications with millions of virtual threads, could still lead to memory overhead. It's generally best practice to design your concurrent tasks to be as stateless as possible and pass necessary context explicitly, rather than relying heavily on thread locals. By adhering these best practices and understanding these considerations, you can effectively integrate virtual threads into your Java applications, unlocking superior scalability, simplified development, and improved performance for I/O-bound and high concurrency workloads. Let's now consider a broader picture of virtual threads within the expansive Java ecosystem. Understanding their genesis and ongoing adoption provides valuable context for their significance. Virtual threads are a cornerstone feature of Project Loom. Project Loom is an open JDK project aimed at dramatically improving the throughput of concurrent applications by introducing a new lightweight concurrency model to the Java platform. Its primary goals include making it easier to write, debug, and monitor high-throughput concurrent applications, largely through the introduction of virtual threads and structured concurrency. Virtual threads are the culmination of years of research and development, representing a fundamental shift in how concurrency is managed within the JVM. Regarding the adoption of virtual threads in frameworks and libraries, this is an area of ongoing evolution and increasing integration. Since virtual threads became a final feature in JDK 21 in September 2023, many popular Java frameworks and libraries are actively adapting to leverage them. Frameworks are redesigning their internal concurrency models to transparently utilize virtual threads, allowing developers to benefit from improved scalability without significant code changes. For instance, reactive frameworks and web developers are prime candidates for adopting virtual threads to handle connections and requests more efficiently. While specific comprehensive lists of adoption across all frameworks might still be emerging given their relative newness, the trend is clear. The Java ecosystem is embracing virtual threads as the new standard for high concurrency I/O-bound operations. This widespread adoption will further solidify virtual threads as the ubiquitous and indispensable part of modern Java development. This integration into the broader ecosystem means that as a developer, you'll increasingly find that the tools and frameworks you already use will quietly handle the power of virtual threads under the hood, simplifying your work and boosting applications' performance. Let's cast our gaze forward and consider the potential future developments and implications of virtual threads in the Java ecosystem. The introduction of virtual threads is not merely an incremental update. It represents a fundamental shift that will continue to evolve and influence Java development for years to come. One significant area of future development is the ongoing optimization and refinement of the JVM's virtual thread scheduler and runtime. As more applications adopt virtual threads, the OpenJDK community will continue to gather performance data and identify areas for further enhancement. This could lead to even more efficient parking and unparking mechanisms, improved handling of edge cases like pinning, and better diagnostic tools for monitoring large-scale virtual thread deployments. Another crucial implication is the potential for simpler and more powerful concurrency constructs built atop virtual threads. With the underlying complexity of thread management largely abstracted away, future Java APIs and libraries could offer even higher-level abstractions for concurrent programming. This might involve more declarative ways to express parallelism or more robust framework for building highly resilient and scalable distributed systems, all implicitly leveraging virtual threads. We can also anticipate a continued and deeper integration of virtual threads into existing new Java frameworks and libraries, as frameworks like Spring, Quarkus, and various other web servers further optimize for virtual threads. Developers will experience transparent performance gains without needing to rewrite significant portions of their applications. This will lead to a more natural, scalable Java ecosystem, where high concurrency is the default, not an advanced topic requiring specialized knowledge. Furthermore, virtual threads pave the way for new architectural patterns in Java applications. The ability to spawn millions of lightweight threads for I/O-bound tasks can encourage a more fine-grained thread per requests or thread per connection model, simplifying design and making applications easier to reason about. This could lead to a resurgence of blocking-style code in scenarios where asynchronous programming was previously mandated for scalability. In summary, virtual threads are poised to profoundly impact how Java's applications are designed and built. They offer not just a solution to concurrent scalability challenges, but also a robust foundation for future innovations in concurrency, ultimately making Java an even more powerful productive platform for building high-performance concurrent systems. This marks the conclusion of our deep dive into virtual threads. We've covered their core concepts, how to implement them, their benefits for handling blocking operations, and their promising future within the Java ecosystem. Virtual threads represent a powerful innovation in Java concurrency, offering increased throughput, reduced resource consumption, and simplified concurrent programming. They empower you to build highly scalable and responsive applications with unprecedented ease. Now, the true learning begins. I encourage you to experiment with virtual threads in your own projects. Try them out, feel the difference, and unlock the possibilities. Also, we thrive on your engagement. Please share your experiences in the comment section of this video. Ask any questions you have, or suggest new topics for future videos. If this video has brought you some value, please give it a thumbs up and subscribe to this channel to get notified about new videos around topics like the one in this video. Thank you very much for watching. My name is Gene, and we'll see each other in the next video.